Thank you for joining us today as IntelliMagic shares practical strategies for optimizing data storage in IBM Spectrum Virtualize Environments. We've packed a ton of helpful insights into this webinar, and we'll be sending you an email with the recording. We do encourage you to ask questions during the presentation, and at the end of each case study section, we will answer them, and then as time permits, we'll answer some more general questions at the end of today's presentation. We are going to give away one $25 Starbucks gift card for questions asked, so you might be the winner. The winner will be contacted this afternoon. Just make sure you submit your questions, and maybe you'll win. Our presenter today is Brett Allison, who is the Director of Technical Services. Prior to joining IntelliMagic in 2010, Brett spent his career in various technical and leadership roles focused on infrastructure and application performance and scalability. At IntelliMagic, he leads the technical service team in the Americas. He delights in helping our customers realize value from using IntelliMagic solutions to gain operational efficiencies and reduce risk in their infrastructures. Brett, I will go ahead and pass it to you to get us started.
Welcome, everyone. Thanks for joining us. I'm going to go ahead and start by putting on the camera just for this short introduction. So, thank you for joining us. I see people on from Germany, and I see some old names on there and also some new names. So thank you for joining us today. We're going to talk about a few different items today, just things that have happened and that we've observed in Spectrum Virtualize environments. And so some of these stories you may relate to, and other stories may be new. I'm going to just start us off with a little bit of an overview story. Several months ago, it was actually in February, we had our team in town, and we had a tech week, and we kind of go over a lot of the different issues that you probably have on your team meetings. But one of the things that we did during that tech week was that we would go out every night and try to do something fun, team building kind of thing. And one night, we had the opportunity to go to Top Golf. Now, not everyone knows what Top Golf is, so I'll just give a little bit of an explanation. Top Golf is a kind of a fun place where adults can go and play golf, and it's a little bit like a combination of golf and bowling and pinball, but they put RFID tags into the balls, and then you play in different holes that are out in this field, and it's kind of like a driving range in that you're trying to hit in these holes from a set place, and then your scores show up like on a bowling alley. You get your name, and the scores show up, and so combine that with some food and some adult drinks, and it's a pretty fun place to go. So we were going to go out there. We all left about 5 o'clock, and several of us got there in about 26 minutes. The car that I was driving got there in 26 minutes. There were some other vehicles that arrived about an hour after that. And so, you know, it was a little bit upsetting for me because we had a limited amount of time, and it was really important that we could spend that time together bonding. And so turns out that they had difficulty getting there, right? So just as a informal kind of survey, feel free to just type in your answer here. Does anyone know why I was able to get there in 26 minutes and the rest of the group, or at least several of the cars, were not able to get there in 26 minutes? Now, actually, no, some of my consultants are on this call. You're not allowed to answer this because you do know. But I'd like someone to just give it a guess. Anyone want to guess? Just type it in the little chat window. If I don't get any responses, I'll go ahead and give you the answer. So we got to wait a few seconds. Nobody wants to guess? There's no wrong answers here. All right, let's see. We got a guess here. All right. I had the right navigator. That's a really good guess. And actually, you're right on. So called in a fire, followed the truck. That's a good guess. But the actual the right thing is I had Google Maps running, and it alerted me that there was traffic congestion, and it rerouted me around an accident on the freeway. And so I was able to go around, completely bypass the accident on the freeway. And it wasn't that information was so hard to get. Other people had access to it, but they kind of knew the right way to go, and so they didn't tie into that. A lot of what we do in performance analysis and optimization and capacity planning. A lot of it is just about having the right information, but really what that tool allowed me to do is it took something that was unpredictable if I didn't have the information and made it predictable. And a lot of the stories that you're going to hear today kind of are revolving around that. We're looking at something, and what we try to do in IntelliMagic is we make the unpredictable predictable. So thanks for your guesses. There were some good guesses in there. The right one was really the navigator, and I was using Google Maps, not the actual driver. I didn't have any special anything special about me. All right, so I turned off the camera so that I won't be a distraction as we go through here. A lot of you guys are familiar with Spectrum Virtualize. You've been using it in your environments, or you have clients that use it. Basically, you have an in-band virtualizer called the IBM SVC or Spectrum Virtualize software that can run on several different types of hardware now. And it's connected to the fabric switches. The servers are also connected to the switches. And then on the back end, you have some kind of storage. All right, so we're going to deal with several different use cases. The first one is dealing with bullies. The second one is downstream congestion. Then we'll look at, is compression worth it? Then we'll look at optimizing SVC for IBM Flash. And lastly, we'll look at optimizing HDS behind SVC. All right, so does anyone know who these bullies are on the left? Just type it in the answer if you know the bully on the left, and tell me the name of the movie. Anyone know that? Type it in if you know it. If you don't know the bully's name, how about the name of the movie? Any guesses? All right, we have a guess. All right, Karate Kid. Good job, Lynn. All right, everyone's got the movie. That's great. I see a lot of you guys got it. So, and then on the right, it's Back to the Future. That's right. So the bullies' names were Johnny Lawrence was the guy on the left, and Biff, that was the guy on the right. So we all have our own bullies in our own environments, right? I mean, this is just something that you have big applications. They're the most important, and they don't care who they run over. And so I'm going to talk through a case study here where we had a bully in this environment. What we have here is a dashboard, and it's the SVC front-end dashboard looking at the metrics that roll up to the front end of the SVC. There's several things going on here. On the y-axis, I have different storage systems. And along the x-axis, I have the key availability metrics. I'm going to focus in on SVC001. I see that it's got quite a bit of front-end read response time, high front-end read response time, and front-end response time, and front-end write response time. And I know that because I've got some big red dots. And big red dots usually mean bad, and particularly in the IntelliMagic Vision tool, big red dots are a bad thing. So usually that means you've kind of entered this critical state where you've got availability impacts. Some people, if not everyone on that SVC, are feeling a performance issue. So we're going to drill down on this. If we know we got a problem, we want to see where it's coming from. So I drilled down to this next level, and the next level is the storage pool level. Now, I'm going to go ahead and focus in here on this pool here, and this happens to be the one that I'm interested here. It's abbreviated, but it's Flash EP Flash _3, and we're missing a little bit of the Flash part. But I'm really concerned about that one, not because maybe it has the biggest red bubbles, but because that's my Flash pool, and I would expect better performance from Flash. So I'm going to go ahead and drill down on that one. And what I see here is I see a series of charts that reflect the higher level metrics that we saw in the dashboard previously, but give us more details over time. And we'll notice that our front-end read response time rating here is 0.28. Now, the rating is just a way to evaluate and assess risk in that environment for that component. And so I've got a couple different ratings here. This is a warning rating for the front-end read response time, and the overall response time of 0.56 is for the overall response time. So what I want to do now is this is the front end. So I know that any IOs to that pool are experiencing really pretty high response time, and it's a flash pool, so that kind of doesn't make sense. So I want to do a couple things, and some of you more astute folks may have noticed this fast write bypass is really high, and the front end write response time is also high. I'm actually going to leave that. I'm tabling that. We'll look at that in a later case study. But for now, I'm going to drill down, and I want to see what the back end looks like. So I take a look at the back end metrics, and this is in SVC, this is the external read response time for that flash pool. Now on the y-axis, we have the milliseconds from 0 to 2 milliseconds. And you'll notice that we'd never get over 0.7 milliseconds. So the back end is not the issue. So now I want to know what is the workload. So I want to look at the read and write throughput for all of the pools. This is a stacked area chart. That purple area is the EP Flash 3. And I can see that I've got over like 1,500 megabytes per second to that pool at times. So I'm drilling down to the volumes that are on that pool. And in this case, I see a very interesting pattern. I see 4 different volumes. And they are actually anywhere from, they're all hovering around 100 megs per second. And those 4 volumes I've got highlighted. They're volumes ending in 125, 202, 124, and 57. So I want to know which host those are associated with those volumes. So I just drill down to the identify, and I see it's a bunch of, there's actually 4 volumes. They all relate to systems that have a prefix of AIX. And so we dug into this. We identified that it's an AIX Oracle system. The volumes residing on that system were Oracle tables that did not contain indexes. And so we asked the DBAs to create indexes, and what I'm going to look, after this was fixed, we're going to kind of jump ahead and look at after that those indexes were added, what happened. Okay, so this is the read and write throughput for the volumes to the EP Flash 3 pool. And you'll notice those 4 bullies that were there before are no longer present. What we have here is a lot more common kind of view. Now, we changed the throughput, right? But did that affect the response time at all? Did that impact the front end? So this is a comparison chart. This allows us to compare different time frames for the same component. And we're comparing the front end response time for EP Flash 3. And the chart on the left was from when we had the problem, when those volumes were bullying the environment. And the chart on the right is showing after they were removed. So on the left, we can see up at the top, we see that the change was 18.45% lower. That's the percentage lower. And the absolute change was 0.45 milliseconds. The other thing is that we drop, you'll see a yellow border on the left chart and then a green border on the right chart. We actually moved from a warning state to a healthy state. So just to summarize, that's, you have to, sometimes you have to deal with a bully. There's different ways to do it, and IntelliMagic gives you a lot of insight into what is happening in your environment. In this case, we did basically we optimized the I/O and reduced the amount of I/O that was going to those volumes. So there's several different ways that you can do this. You could optimize queries, add indexes like we did. You could do some over-the-top things like adding some I/O governance. And kind of as a backstory to this, I had actually already gone through that process. These volumes were doing 300 megs a second, and we kept lowering them down to 100 until we got to 100, and then we kind of got to root cause after that. So the other option, if you can't deal with them, is to give them their own environment. All right, so we're going to switch gears. We're going to look at some downstream congestion. Does anyone's commute look like this? I hope not, but I'm afraid that many of us do have a commute that looks like this oftentimes. When you have an accident on the freeway, even if it's 5 miles ahead, that can oftentimes cause delays where you're at on the freeway. And so the same thing applies to SVC. A lot of times the SVC will get blamed for it, but what you're dealing with a lot of times is something that's happening on the back end. So we're going to talk about what that looks like. This chart is an SVC Node Dashboard. It's looking at all of the SVC metrics. And we have the key metrics across the top, and then we have the controller names along the y-axis. In this case, I really want to hone in on South SVC 001 for this exercise. So we're going to drill down on South SVC 01. It's got some front-end read response time, some read hit, and some front-end write response time issues. When we drill down, we're going to notice a series of charts that are over time. These charts represent each of the nodes within South SVC 001. The node read response time is what I want to hone in on. And I see there is a very tall gray line. I want to make this chart bigger, so I'm just going to blow it up. And what I see here is a gray line that relates to node 7 that is much higher than the rest. So I kind of want to drill down and see what's going on there. So this is, again, this is the read response time on the front end of this node. And when we drill down to the volumes associated with this node, I see really two volumes that stand out, and they're actually in bold in the legend. The one that has the highest number, the highest rated risk here is volume 006, and that's the green line. And I'm going to drill down, and I want to look at the front end read response time as well as the read miss IO rate. So for this particular volume, I've added a chart that is the read miss IO rate. And what this is telling me is that, you know, I've got response times up around 120 milliseconds, and guess what? It correlates to the read miss IO rate. So that tells me that I'm not spending extra time on the front, but for every time I have to go to the back end, it's taking me a while. So let's drill down to the back end. So I see that it's on South DSS Tier 201. So I want to look at the back end of that pool. And this is showing me the managed volumes or the managed disks for this pool that's having problems. So I've just blown this up, and I see the queue time on this pool is very, very high, anywhere from 40 milliseconds to over 100 milliseconds. And the read response time it's a bit hard to see, but it's 10 to 20. So this is my culprit. I've got back-end queue time issues here and back-end response time on this particular storage pool. So how do you deal with the back-end congestion? Well, you can add more lanes, NDIS or disk drives. You can add faster lanes, so you could put flash in there, or if it was nearline SATA, maybe you could put some spinning drives there, or you could limit certain workloads, and this is kind of that over-the-top, make people do less even if they don't want to, or you could add an HOV lane. So this is IO priority queuing, currently only available on the DS8000. The reason I mention it here is that it's been requested by IBM to put it in the SCSI T10 standard. So that would be a great thing if they could push that through. That was something that I had pushed for about, I guess it's been 8 or 9 years now that I pushed for that originally on the DS8K. It finally got done on the DS8K, and they're trying to make it a standard. So that's kind of an interesting one. Hopefully that will get in the SVC at some point in the near future. All right, I'm going to switch gears, and I'm going to talk about compression. You know, compression is meant to reduce the amount of volume required to contain something. You remember that expression? You can't get something for nothing, or nothing in life is free. It's similar to compression. So just like this man has chosen to wear a very tight-fitting compression shirt to manage his volume, SVC is able to fit more bits into a smaller space with compression. But there's a cost, and that's CPU overhead. On newer hardware models, the DH8 and newer hardware models, it's not usually an issue, but I'm going to show you an example where the cost outweighed the benefit. In this next slide, we'll take a look at the SVC Node Dashboard that I introduced you in the previous case study. So this Node Dashboard, we've got several systems here that are showing performance issues. I really want to hone in on the SVC 001 again. It's got really high node utilization. It's got front-end write response time issues. So I'm going to drill down on this one to the node over time charts, which I've shown previously, and I see the node utilization on this guy, and I've got very high node utilization, and in particular, this node utilization is for the node 3, and it's got a rating that is higher than most of the others of 227. Node 4, its partner node, actually has a rating that's a little bit higher, but we're going to focus on node 3 because we want to know what's driving the load on node 3. So I'm going to stick with node 3, drill down to the throughput on node 3, and then you can see it's the yellow throughput. I don't want to see which volumes are driving the load. And it turns out that I've got some pretty heavy-hitting volumes here. Most of these heavy hitters we drilled down on, and they were compressed volumes. So now what we're going to do is take a look at what happens when we remove those volumes. This is the node utilization. We'll look at the node utilization first. This is the node utilization on the left when those compressed volumes were active. And then on the right, this is when we got rid of them. And you can see on the left very, very high peaks. On the right, it's much more reasonable. The change was a 37.45% reduction, and the absolute change was 24.28%. So we almost saved a complete core when we move those compressed volumes off. In terms of response time, there was a slight improvement in response time. It didn't make a major dent on it, but it did make a 20% overall improvement. The absolute change was almost a millisecond. So it was noticeable, measurable improvement. All right, so was the compression worth the space saved? In this case, I'd say no. You want to look for high node utilization, and you want to examine whether or not the active volumes are on the busy nodes and if they're compressed. If the active volumes are compressed, they may not be the best candidates for compression. All right, so we're going to switch gears. We're going to look at optimizing IBM Flash behind SVC, and this was a very interesting case study that we did, looking at some observations that around the cache settings. So normally, when the write cache is enabled during normal operations, a host write will enter an SVC node's cache, and then it will be sent to the partner node. Upon completion of the write to the partner node, it's going to be sent to the host, and then the write eventually will be destaged to the backend flash. I see that there's a question. I'm going to go ahead and pause, and I'm going to pause at the next end of the next case study. I'll pause and I'll take some questions. Okay, so if you have some questions, go ahead and ask them. I'm going to keep going with this case study, and then I'm going to pause at the end of this case study. All right, so with SVC write cache disabled for a volume, the write is actually going to pass through SVC and go to the backend controller. And in reality, there's some communications that happen between the SVC host and the backend that I didn't include to keep it manageable. But in general, you're going to bypass the node cache, and the writes are going to have to be destaged before they're acknowledged as completed. All right, so I want to look at what happened when we had the cache enabled. So on the left side, we have the cache enabled. And during that time, we see, okay, we see some pretty big spikes, okay response time. On the right side, we have the cache disabled. And what we observed in this was an increase when the cache was disabled of a 94.38% in terms of the front-end write response time, with an absolute change of 1.87 milliseconds. So for this workload, disabling the cache was not helpful. All right, so I'm going to pause here. I've got a couple questions. And someone asked on the compression one if the SVC that we looked at was one with two processors. So this was an older, it was a CG8, and it did not have the additional processors. So that's a very astute question, and it sounds like you had some experience with something similar. So definitely on the old, if you hadn't upgraded those CG8s to have the extra processor, which I think was an MES at one point, then you could get into a situation where you just didn't have enough horsepower. All right, so are there any other questions on any of the case studies that I've done to this point in the presentation? This would be a good time to just ask them. Okay? All right, I'm going to go on to the next slide. So this is our last case study, and this is HDS behind SVC. Does anyone remember this car? Who can tell me the name of this car? All right, let's see if we got some answers here. All right, yes, it is a DeLorean. Good job, Peter. All right, Jim got it too. All right, we've got some very astute folks on the line. So sometimes when you get a car from the factory, it doesn't do everything you want it to do. The same thing is true for the SVC and the backend storage. Sometimes you have to make some tweaks. And if you don't, there's actually some pretty significant ramifications. So, you know, we've looked at this diagram. Essentially, in this case, we've got HDS behind SVC, and we've got a front-end dashboard. And that's showing you what the hosts are experiencing on the front end. And so in this case, everything looked great for SVC01 and SVC02. But when we looked at the back end, and that is the SVC's perspective of its communications and response time and relationship with the back-end storage, SVC01 looked really bad. We had a ton of external read response time and queue time. And SVC02 looked really good. All right, so when we look at the queue time over time on SVC01, we do see spikes where it's up around 2.6 milliseconds. Now I'm going to drill down from here, which is at the pool level, to the managed disk level. And I see lots of NDIS here, and you can look in the legend. They all have SSD on them here, and they're all showing very high queue time. Now, how does that make any sense? Why am I queuing on that device? So really, there shouldn't be any reason for queuing on that device. So what we actually did in this case was we dug down into how those volumes were set up and what was the difference on SVC01 and SVC02. Now, do we have anyone that wants to guess what the difference was in terms of the configuration settings on the SVC controller for those volumes that were associated with SVC01, are those MDIS on SVC01 and those MDIS on SVC02? Does anyone know? Any guesses? Give it a second. Just type it in if you have a guess. No guesses? All right. So the difference was the host entries. The VSP host entries for SVC were set to standard, which is the default, and they should have been set to Windows. Once this was changed, the clearing completely cleared up and everything was green again. So that was the big difference, is you need to set those to Windows and not standard, which is the default. So I hope these case studies were interesting to you. What I would like to see, if anyone would like to have myself or someone on my team look at your data and see if we can find anything not only interesting, but any kind of availability risks in your environment, please reach out to me. My email is brett.allison@intellimagic.com. You can just send me an email. I'll be glad to set it up so that we can take a look at your environment and see if there's any availability risks or case studies going on in your environment. Do we have any questions? So at this point, I'm not seeing any questions. So I'm going to turn it back over to you, Danielle. Or we're basically, I've gone through the content. So unless there's any questions, I'll go ahead and wrap it up.
Yes, thank you again for joining us today. We hope you found this webinar helpful. You will be receiving an email from IntelliMagic with a link to today's recorded webinar, with some additional resources that we hope you find helpful to optimize your Spectrum Virtualize environment. We do build our products around what helps our customers, and we do appreciate your feedback. So any feedback you'd like to send over to us, please send it over. Thanks again, Brett Allison, for presenting today, and from all of us at IntelliMagic, thank you for attending today's webinar.
Thanks, guys. Take care.